Okay, so welcome back for this session. We have two talks. So the second talk would be online by Sergej because unfortunately there was some medical emergency for which he couldn't travel. So we will have him online. So the first talk would be by Ajit Balram from Institute of Mathematical Sciences, and he would be talking about exact volume law entangled zero energy eigenstates in spin models. Ajit.
Okay. Should I start? Okay, so let me start off by thanking Subhro and Sergej for putting this very nice program and for inviting me to speak here. So I'll tell you about exact volume law entangled zero energy eigenstates in a large class of spin models. This is work done in collaboration with Sanjay Maudgalya and my graduate student Sashikant Mohapatra, both of whom are in the audience. So Sashi is on the postdoc job market, and keep an eye out for his application. And the main reference for this work is this article that was published last year. Okay, so I'm going to give a very quick introduction to ergodicity and thermalization in isolated systems. And then I'll come to the main part of the work, which is discussing some spin Hamiltonians and how they can host some exact zero energy volume law entangled states. And I'll end with some summary and future outline. So one can ask this question, does an isolated classical system actually thermalize? And generically, the answer to this question is yes. So if you take, let's say, the classic example of this is a billiard stadium and a ball. So let's say you start the ball in some position with some velocity. Then eventually, if you just track where the ball is going, the trajectories will fill up the whole of the billiard. So for any generic structure of this billiard, you will find that these trajectories will completely fill up the full space. And all the memory of the initial condition is completely lost. So all of the phase space will be fully explored. And this where you started the ball from with what velocity, that information is completely lost out. There's also a chaotic motion that the billiard shows up. So what are some examples where this does not happen? So for example, in integrable systems, such things don't happen. So there's no thermalization in integrable systems. And that's because of the presence of conservation laws or symmetries, so that you get some stable periodic orbits. So here are some illustrations. So let's say you take a circular billiard ball and you start the ball at a particular angle, exactly at this angle. Then you get these like periodic triangular orbits. Or let's say you start the ball in this trajectory where you just go straight up. Then you get this like square orbits. And you never leave these. The ball will always remain on this orbit forever. And in these like nice billiard stadium, which are like circular, there are many of these trajectories where you keep getting periodic orbits. So in these cases, the particle fails to explore all of the phase space that's available to it. But the thing that tends to be the case here is that these are extremely fine-tuned. So let's say if I put an obstruction in this billiard, or I change the shape of this billiard slightly, eventually the particle will go on to explore all of phase space. Okay, so what about in quantum systems? So similar to classical systems, generic isolated quantum systems are also chaotic or ergodic in nature. But because Hamiltonian evolution is unitary, the initial states, the initial state information always remains. So because psi of t just goes into e to the minus iht psi of 0. So here thermalization is actually like a subsystem phenomenon. It happens locally. So let's say if I look at some small part of the entire system, then the rest of that system acts like a bath for this subsystem. So for any subsystem, the rest of the system can act as a bath. The system as a whole evolves unitarily. So there is no notion of thermalization for the entire system, but it happens locally. So here is an example. Let's say I take a spin chain or particles on a 1D and look at, let's say, this subsystem A, which I marked A, just two sides. Then the rest of the system B acts like a bath for this system. So if you look at the reduced density of matrix of A at very long times, then that goes towards thermal distribution. And these properties are usually for some generic state in these systems. So we're not looking at like very special states, which are like ground states or some low-lying excitation. So if you just look at states in the middle of the spectrum, then you would see that properties of this kind would hold. And how is thermalization governed? So there is a hypothesis, which is called this eigenstate thermalization hypothesis, which says that every eigenstate of a thermal system is thermal. So if you look at like expectation values of local observables, then they are given by the standard expectation in a thermal ensemble. Okay. So concomitantly, thermalization actually goes hand in hand with entanglement. So in general, if you ask how does the thermalization grow in a chaotic or ergodic system, then the entropy, the entanglement entropy of these systems goes as like volume law. So if you just look at a small system, then it's like densely connected to all the other to other members of the other subsystem. So one entanglement-based diagnostics for this chaos or ergodicity is that if, let's say, I look at what is the entanglement entropy as a function of the size of the system. Let's say you just look at 1D, and the system size grows as, let's say, L. Then this entanglement entropy will go as L. So in 1D, it will just go like volume. So that's just length. Whereas if you look at like MBL systems or systems which evade thermalization, then this entanglement entropy is usually sub-extensive. So for example, in 1D systems, typically you see a logarithmic growth, sometimes even like constant. But what I'm going to show here is that this notion alone of entanglement entropy growing as volume law may not tell you that the system is actually thermal. So you can have some atypical thermal, atypical states which have entanglement entropy which does go as volume law. And usually the issue with this sort of thing is that constructing these states is extremely hard. So if you have an entanglement entropy that grows as volume law, then you need a lot of information to actually capture this state. And so constructing states of this kind is very hard, and that was like a motivation for us. So can we give an exact construction of states of this kind? So a couple of examples that were known before our work. So this is a very famous example of what are called rainbow scars. So these states actually have this property of having volume law entanglement. So what you do in the rainbow scars is you take, let's say you take a 1D lattice and you look at states that are related by this mirror reflection. So let's say states 1 and 8, 2 and 7, 3 and 6, 4 and 5. These all share a bell pair between them. So this notion is a singlet state that you form between these. So it's clear now that this state has volume law entanglement. Why? Because let's say I look at the entanglement entropy of, let's say, these 4 sites with the rest of the system, then that's exactly 4 log 2. Because I cut exactly 4 bonds. And in general, if you, let's say, take any bipartition where you have only one side of the 1D lattice, then this will have volume law entanglement. Let's say if I take these 3 in 1 and these 5 in 1, then this will go as 3 log 2. But the interesting thing is that not for all bipartitions this is true. So let's say I have a bipartition where I take these 4 in between and look at what is its entanglement entropy with the rest of the chain, and that's exactly 0 because all the bell pairs reside completely inside this. There is no bell pair that goes out of this subsystem. So for certain selected bipartitions, and these bipartitions can even be contiguous. For example, these 4 sites are together, but even with these contiguous bipartitions, you can have entanglement entropy which is not volume. The other thing is that these states also show like fairly like anomalous correlations for even local observables. So if I, let's say, look at the spin-spin correlation here, or let's say look at the spin-spin correlation between these 2 points, then they'll be exactly correlated. So they are atypical in that sense. And the other issue is like usually getting these states as some eigenstates of Hamiltonians is fairly difficult. So for example, this rainbow scars happens to be an eigenstate of a fairly complicated Hamiltonian. It's an XYZ spin chain with some nearest neighbor ZZ interaction. Another example that is known is what is called entangled antipodal pair states. So in this, what you have is that you put the 1D system on a ring and you make bell pairs between antipodal points. So these 2 are in a bell pair, these 2 are in a bell pair. All of these antipodal points share a bell pair. And this bell pair is just 0, 0 plus 1, 1. Entangled antipodal pair. So again, it's fairly obvious that this state has volume law entanglement because if I, let's say, take a subsystem where these 3 sites are included, then this has entanglement entropy, which is 3 log 2 because I cut exactly 3 bell pairs. And the other thing is that's easy to see is that if you look at the reduced density matrix of this, then it's completely uncorrelated with the rest of the system. So its reduced density matrix is proportional to identity. So this is the same as the infinite temperature. So here actually it turns out the Hamiltonian is fairly easy to write. So the Hamiltonian for which this state is hosted as an exact zero energy eigenstate is this Hamiltonian J1 sigma x sigma y. It's a purely imaginary Hamiltonian written in the computational basis, and then J2 sigma y sigma z. So I will show why this is the eigenstate of this Hamiltonian. Okay, so enter the main result of our work. So what we showed was that you can have a fairly generic construction of zero energy entangled, volume law entangled states. So we consider a class of spin S chains of size L with translation invariant interaction with means periodic boundary conditions. And you look at Hamiltonians of this kind. So there's a sum over alpha. So alpha tells you what all kinds of terms you have in Hamiltonian. And you run from sites 1 to L. And you look at like n spin interactions. So each of these terms, H alpha, is an n spin interaction. It's a product over n spins. The spins can be raised to some power q in general. These are our standard spin S operators. And this interaction encodes an interaction between n spins, which are at these particular sites, I plus J1 to I plus Jn. And I define this Hamiltonian in the standard Hilbert space of 2s plus 1 to the power L. So every site has 2s plus 1 dimension, and you raise that to the power L. And we're going to use the global computational basis. So let's say if you have two sites, then this computational basis is just 0, 0, 0, 1, 1, 0, 1. Okay. That's all. So what all Hamiltonians actually fit this criteria? So one thing is that any spin half Hamiltonian can always be written in this way. So why is that? So the thing to notice is that at every given site, I only have a particular spin. So the nice thing about spin half operators or polymatrices in general is that the product of any polymatrices gets reduced to a single polymatrix. So if I have any product of polymatrices at a given site, that would be reduced to a single polymatrix. But that's not true for higher spins. So for example, here is an example of a state that, of a Hamiltonian that fits our criteria. So let's say I take SI x square, but I take SY at a different site, I plus N. Things like this are perfectly allowed. But if you take spins of this, Hamiltonian terms of this kind, which is like SIX, but SI at Y. So at the same site, I have both X and Y, then this will not fit our bill. But for spin half matrices, this will again get reduced to SZ, so then it's okay. But otherwise, in general, this does not exhaust all possible Hamiltonians that you can write for higher spins. But for spin half, any Hamiltonian can be recast into the form that I gave. Okay, so what is the criteria that the Hamiltonian needs to meet? So if each of the terms, of each of these terms, which we call these local terms, anti-commutes with an operator, which is C times K. So K here is the standard complex conjugation operator. And C, for the purposes of this talk, you should just consider C to be a product of unitary operators. Each of these operators are on-site operators. So if each term of the Hamiltonian anti-commutes with C times K, then I claim that there is a state that you can write down, which is lambda C, which is for a system of size 2L. So I started with a system of size L, and from that I can write a state which exists in a system of size 2L, so twice the size as the original system. So this, I formally write it down as like C S1 to L times S bar, S1 bar to L bar. So when I say I bar, I mean I plus L. So every bar is connected to L sites away from it. And this state, which is just sum over all spins at, sum over all the states at the local site, I'm going to show is an exact zero energy state of the Hamiltonian, defined on size 2L for a system with periodic boundary conditions. No, it won't be, so you will see in general. Yeah. What is Q? That's only for spin half, no? You're only talking about spin half. So in general, this C doesn't even have, I mean, this is not just defined for spin half. This is true for any spin S. What is C cube? But many cases, so let's say if you have spin half, then the C cube will get reduced to C. So you may not get an independent condition from that. So let's say C happens to be sigma Z, then sigma Z cube will get reduced to sigma Z. So you may not get an independent operator by cubing. Yeah, then you can have another state which is of this kind. That's perfectly fine. But usually we will find that many of these are not independent. You will keep reducing to the same state. Okay, so the way this zero energy thing happens is there is a cancellation that happens. So if you look at the Hamiltonian's action on the state lambda, on the sides I plus J1 to I plus Jn, that term will be precisely cancelled by the action of the Hamiltonian on sides I plus J1 bar to I plus Jn bar. So remember, by bar, I mean this index with L added to it. So these two will exactly cancel each other. So you'll get a pairwise cancellation of this kind. And because C is a unitary operator, this will generate particle hole symmetry for you. So if the state is at zero energy, it's also a mid-spectrum state in these problems. And that's why this will end up being a zero energy state. Okay, so the proof is fairly involved and complicated, but instead of giving you the proof, I'm going to just explain, I'm going to give you an example where you will see this in action. Okay, so let me first pictorially show what the state looks like. So what you do is that you form some dimers between antipodal points. So in this example, I have a nicely ordered 1D chain, which is put on a ring. And I have bell pairs that go between sites 1 and 1 bar, 2 and 2 bar, 3 and 3 bar, and so on. So by a dimer, I mean I have a configuration of this kind. It's site I have S, and then at site I bar, I have C times S. Okay, so another thing is that you don't even need this to be in a nicely kept configuration like this. You can have a fairly disordered system. And as long as you make these pairwise dimers, you'll find that this cancellation holds. So it doesn't even have to be in a very ordered solid. You can have an amorphous system which will respect this symmetry. Okay, so what is it that you need to do? So let's say I have a bunch of operators C1 to CL on the system of size L. Then I have to keep those as it is, and on the next state from, let's say, L plus 1 to 2L, I have the identity operator. So I make a state which is like C times I times identity times I bar. So that's the state I need to make. And the important thing is this C times complex conjugation anti-commutes with every on-site term. And this will make sure that this state is a zero energy state of the entire Hamiltonian. Okay, so first let me show that this state is actually volume law entanglement. That's fairly easy to see because this lambda state is just a product of dimers between bonds I and I bar. So if you make a contiguous system of n sites, then that is going to cut exactly n bonds. Okay, so if C happens to be unitary, then the entanglement entropy, let's say for a spin half system, is exactly n log 2. You cut exactly n bonds, and there are, in that case, this will be like bell pairs, and you cut exactly n log 2. I mean, n log 2 will be the exact entanglement entropy. Okay, so one interesting thing is that for local observables, this state actually happens to be thermal. And simply because of this like an EAP kind of state, that there is no correlation between these neighboring or like, there's no correlation between any set of sites which are separated with less than size L minus 1. So all these are completely uncorrelated. So if you look at the reduced density matrix on this, then it'll just be proportional to the identity matrix. But an interesting thing is these states are still atypical because if you look at some like non-local but still few body observables, they will be perfectly correlated. So if I look at the spin-spin correlation here, it'll be like perfectly correlated. And again, if you look at like tailored subsystems, just like in the rainbow scars, you now have, let's say you look at tailored subsystems which are not contiguous. So you look at bipartitions which are not contiguous, then you can get anomalous entanglement entropy. So for example, let's say I took the subsystem to be made up of sites I and I bar. So this is the subsystem and the rest of it is the other subsystem. Then the entanglement entropy between these two is exactly 0 because there are no bonds that go away from this subsystem out to the other subsystem. So for tailored subsystems that are chosen to strictly consist of sites I and I bar, this entanglement entropy is exactly 0. Yeah, and the important thing to keep in mind is that you can have like non-local but few body observables which are highly athermal in these states. Okay, so one interesting corollary to our theorem is that if you look at this state, lambda I, so you choose C to be I. Okay? Then this state is always a zero energy eigenstate of any Hamiltonian, which was given in the previous slide, which has a purely imaginary representation in the computational basis. Because if you had an imaginary representation in the computational basis, then just complex conjugation alone anti-commutes, right? Because just complex conjugation will change the sign, and you can just choose C to be identity, and that will do the job. So this is exactly the state lambda with C set to be identity, and for this, the anti-commutation will hold, provided the Hamiltonian's representation in the computational basis is purely imaginary. So it turns out that this entangled antipodal pair state is exactly of this form. So you look at Hamiltonian, which is of this kind, sigma 1, sigma I x, sigma I plus 1 y. So any spin half Hamiltonian which has an odd number of sigma y's in it is purely imaginary. Right? You can only have either even number of sigma i's or odd number of sigma i's. If you have odd number of sigma y's, then this is a purely imaginary Hamiltonian. And the corollary to our theorem says that if you have C to be identity there, then that state will be an exact zero energy state of this. So this state indeed is this Hamiltonian is indeed purely imaginary. So you can just set C to be identity and you get an entangled antipodal pair state. So there, what do you have to do? The way you make the state is you have you let's say have 0 here, then this will also be 0 because it's C times 0. So C is identity. So it's the same state on the antipodal side. So this will be in a bell pair which is 0, 0 plus 1, 1. That's exactly this bell pair. And more generally, as I said, if you have any Hamiltonian with an odd number of sigma y's in it, then this state will be a zero energy eigenstate of it. Okay, so let me now give you an example of how this cancellation actually happens. So for this, I'm going to pick the spin half XY chain. This is actually an integrable model, but it's useful to keep this in mind to see how the cancellation goes. So what is the Hamiltonian? So the Hamiltonian is J1 sigma I x, sigma I plus 1x. So this is the XX term. Similarly, you have a YY term. And then you have a term which is like sigma Z, which is just the field put in the longitudinal direction. So now what I do to go back to my theorem, I consider this as being composed of 3 kinds of terms. So that is that alpha. So alpha is 1, 2, and 3 here. So that's the XX term, the YY term, and the Z term. And what I need is an operator C, which times K will anti-commute with each of these terms. Okay, so what is it that I can pick for C? So what you can do is you can look at terms of this kind. So you take sigma x at side 2i minus 1, and you take sigma y at side 2i. So this will actually anti-commute with each of these terms. So why is that? So let's say I take one term which is like sigma I x and sigma I plus 1 y, or sigma I x and sigma I plus 1 x. Then this sigma y will anti-commute with one of these. So that will make sure that this anti-commutation holds. Similarly for this, there is a sigma x from here to anti-commute with, and sigma z anyways anti-commutes with each of these polymatrices. So this operator C automatically satisfies this condition. So here complex conjugation plays no role because this is a purely real Hamiltonian. And now you can write down this state, which is lambda CXY, which is phi plus at I bar and phi minus at I plus 1 bar. So why is it like this? So I have phi plus because I need to make 1 and 1 plus L with sigma x. So it will be 0 and 1 because sigma x flips the spin. So this state will be like 0, 1 plus 1, 0. But on the next state, I have to put sigma y. And sigma y flips, but with a sign. So this state will be 0, 1 minus 1, 0. So I make dimers alternating like this. So I have like, let's say, 0, 1 plus 1, 0, 0, 1 minus 1, 0, 0, 1 plus 1, 0, 0, 1 minus 1, 0, and so on. So the other choice, as Abhishek pointed out, you can make is you turn these two around. You can have y here and x here, and that's basically it. You can't do anything else. At least we haven't been able to find any other operator which will do the job. Okay, so how does the cancellation go? So let's look at how this cancellation proceeds for the XX term. So the Hamiltonian for the XX term is just sigma I x, sigma I plus 1x, that's all. So what I'm going to claim is that if you look at the action of the Hamiltonian on this bond, that action will be exactly cancelled by this bond. That's the claim. Okay. So what is the action of the Hamiltonian on this bond? You have to act sigma 1x on this side and sigma 2x on the other. I mean, you have to act sigma x on these 1 and 2. By the way, this is the state. Okay. So let's look at what happens to this state. So I had originally in this state, this bond was actually 1, 0 plus 0, 1. Okay, so if you act sigma x here, then 1, 0 becomes like 1, 1 because you flip the spin with sigma x, and this state becomes this whole bond turns into 1, 1 plus 0, 0. So that's exactly this bond that's drawn. Remember, this was the original state. So this was like 1, 0 plus 0, 1, and you acted sigma 1x on it, then this is exactly the state you get. Okay, now let's look at sigma 1x, sigma 1 bar x, sigma 2 bar x on this. then what this does is this also flips the spin, but because of the presence of this bond which was already had a sigma y in it, you get exactly the same state but with a negative sign. So you get exactly the negative of this state is exactly this. So basically this and this put together cancel each other out, and that's why you get an exact zero energy state. Okay, so maybe I'll go through this a little slowly. So remember, this was the state which was like 1, 0 plus 0, 1. Okay, and this state is 0, 1 minus 1, 0. So what I have to do is I have to add sigma 1 x, sigma 2 x on this, and I have to add sigma 1 bar x, sigma 2 x, sigma 2 bar x on this. And what I'm claiming is that the action of these two is exactly cancelled. And the same thing will also happen for the yy term. Let's look at the yy term. So remember here, this was the original state. So now essentially these two bonds are actually swapped. So this, the action of sigma 1y, sigma 2y on this state, this produces this as it is, up to, and with a negative sign. So that's why I put the negative sign here. And the action of sigma 1 bar y, sigma 2 bar y will produce this state exactly. And because of this important sign, these two things cancel each other out. So now you can repeat this argument over all the bonds. So every antipodal bond action on every antipodal pair, that gets cancelled out. And that's why this has exact zero energy. And of course, for the last term, sigma z, it's obvious that this has zero energy because it has equal number of up and downs. Okay, so that's the main crux of the argument. There are precisely two terms, and the action of them is exactly cancelled. Okay, so we can now also go ahead and generalize this to arbitrary dimensions, because as I said, it's not very important that this is on a 1D grid and things like that. As long as you have a configuration of bonds which are arranged in a particular way, so that you can engineer this like pairwise cancellation, this thing will be done. So you can have this in like 2 dimensions, 3 dimensions, and so on. So let me give you an example of 2 dimensions. So if you, let's say, look at the 2-dimensional XY model, again with a field, then you start off with this. So I look at this on a rectangular grid. So there are 8 sites here. And again, you can choose the operator C to be like sigma x here, sigma y here, sigma x here, sigma y here. This will ensure that this will anti-commute with the Hamiltonian. So each of these is arranged in such a way, it's exactly like in the 1D case, you had like sigma x alternate with sigma y in both directions. And this will make sure that this anti-commutes with C. So from this starting configuration, you can build a bigger lattice where this state will exist. So these are the bonds. So there is 1 and 1 bar. They share this bell pair. And 2 and 2 bar share this other bell pair, which is 0, 1, minus 1, 0. That's basically exactly the sigma x action on this gives you this red, and sigma y action gives you this blue. And now you can go ahead and like wherever you have A and A bar, for even sides, they make this blue bell pair, and for odd sides, they make this red bell pair. And this you can show will satisfy this condition that I said. So this will be an exact zero energy state of the Hamiltonian. And now you can play a few games and like try to arrange these in funny ways. So this was the original one that we had. You had matched 1 and 1 bar and 2 and 2 bar. But you don't have to necessarily do that. You can put 1 bar and 2 bar here, for example. So the only important thing is that if you look at the surroundings of 1, and you have these bonds 2, 5, and 6 near it, that's also the case here. And near 1 bar, you will have 2 bar, 5 bar, and so on. So these terms have to be similar in nature near the I and I bar term. As long as you have this sort of numbering that you can consistently maintain, you will have these like bell pair states that exactly cancel, that give you an exact zero energy state. And then you can use some lattice symmetries like translations or rotations or reflections to come up with more states of this kind. It's just a matter of which bond you join. So for example, 1 could have been joined with 1 bar here or with 1 bar here and so on. And these give you some additional exact zero energy states. Again, you can go ahead and do this in like 3 dimensions. So again, you can make configurations where you have to just line up numbers in a proper way so that the environment that I and I bar see is roughly the same, so that the bond that I connects with something is exactly cancelled with I bar connecting with something. But an interesting thing that happens in 3D is that for certain bipartitions, Now this will not be volume law entangled. So an example is illustrated in this middle figure. So let's say I look at these 4 bonds. So these are exactly 10, 10 bar, 11, and 11 bar. So these are completely, they only make bell pairs within themselves. So there is no bell pair that goes out of these 4 sides. So in these configurations, there are special contiguous bipartitions for which there is no entanglement between this system and the rest of the system. So it's not entangled, volume law entangled for certain specially chosen, but contiguous bipartitions. So these are contiguous bipartitions, but they don't have volume law entanglement. But for most bipartitions that you choose, so let's say I chose the neighboring one, which was 9, 12, 11, 10, then this will have volume law entanglement because all the bell pairs only go out of this subsystem. Okay, so I'm basically almost done. So we actually uncovered many other examples, and some actually even happen to hold for spin S, which is greater than half. So you don't necessarily have to look at spin half models, but you have these examples even in like higher spin models. So some examples are the spin S XY model, and also the spin S Kitaev chain. They host these states. Also in the PXP model, there are states of this kind. So there's also a spin half model which Deeptiman worked on, which has 3 spin interactions where such states exist. There's also like integrable models, so like this transverse field Ising model where this thing exists. So that's fairly easy to see. The transverse field Ising model is just basically this XY model where you set the YY term to be 0. So if you set J2 to 0, you just get back the transverse field Ising model. And there again, this sort of state is an exact volume law entangled state. It's unclear to us at least as to how to see this in the usual integrable language. Like how does this state look in terms of like Jordan-Wigner fermions? So that part we haven't done yet. Okay, so let me end with a quick summary and outlook. So we constructed a large class of spin chains with exact volume law entangled excited eigenstates. So in all the cases that I mentioned, this operator happened to be unitary. So there was also particle hole symmetry in the problem. So the moment you have state which has 0 energy, that lies in the middle of the spectrum. So that's a nice thing. So it's not a special state like ground states or low-lying excitation. It's right in the middle of the spectrum, and it has this property that it is anomalous with respect to some few body, but non-local observables. But otherwise, it looks very much like thermal. It has entanglement entropy, which is volume law. And for local observables, it looks thermal. So that's the second point. So entanglement entropy and our expectation values of observables alone may not be like good indicators or definitive eigenstates that support or violate ETH, because we cooked up some states which have volume law entanglement, which have local correlations which look exactly thermal, but they're still atypical in the sense that there are special few body but non-local observables which are anomalous. Yeah, and we were able to extend this construction, which was previously known only for like spin half models and for 1 dimension to higher dimensions. So one thing we've been struggling is to figure out how to do this for like fermionic or bosonic systems. So these spins give a nice way of like coming up with these like anti-commutation relations, but we haven't been able to do this for like fermions or bosons. That's an interesting criteria. The other interesting thing is how to go beyond pairing. So can I have like a genuinely L cluster configuration which gives me cancellation? So can I put like 3 spins together and get a cancellation which does not break down into 2 and 1? Or let's say I have a 4 spin configuration which gives cancellation which does not break down into 2 plus 2. So can I get a genuinely L particle clustering where L is greater than or equal to 3? That again, we haven't succeeded in doing. All the examples that I show, they always have this like pairwise cancellation. And also there's this interesting thing of how to find algorithms to find such eigenstates given the Hamiltonian. So let's say I hand over the Hamiltonian to you. Can you tell me if such a state would exist? So, this is analogous to the scar finder searches that these people have looked at. So these are, in a sense, they are like scars, but they are like volume law scars. They are atypical, but they have like volume law entanglement. Usually scars have area law entanglement. They have like sub-extensive entanglement, but they are also atypical in that sense that they're different from thermal eigenstates, which are at the same energy. So how to go about looking for these eigenstates? So yeah, those are things that we haven't been able to sort out yet. Okay, so with that, let me end. I would like to thank Sashi. All the bulk of the work was basically done by him, and also Sanjay for this generous collaboration. And I'd like to thank generous funding from my institute and DAE and so on. Okay, thanks. I'll be happy to take questions.
Questions.
So my question is about the final conclusions and the motivation. So what you demonstrated is that there are certain atypical states that might fool you into thinking it's Eigenstates normalization.
Exactly.
Right? But they're not.
Yeah.
And so you could say, right, great, but there is an easy, like if I'm a numericist, let's say, I could just look for random pairs or random, bipartitions.
Yeah.
And then, with certain chance, I will not be selecting these atypical states.
I agree with that.
So if I'm a skeptic, I could say, well, what's the big deal? You found some very atypical, very fine-tuned states.
Yeah.
Oh, great.
That's a genuine criticism. That's perfect. So our original hope was that we will be able to find many of these. So like you get like exponentially large number of these and try to like go towards ETH with that. But as I said, we haven't succeeded in that. So the number that we get is much smaller. It's usually like order 1. But the idea was like, let's say if you can cook up a model where you can construct exponentially large number of these states, then the chances of hitting them is non-zero. So then maybe there is a way to like show ETH demonstratively in these systems. But we haven't succeeded in that. So that's a fair criticism. I completely agree with that.
Is there a chance to find models where these states appear as the ground state? For example,
great question.
Take the sum of local projectors. So
yes,
we know that ground state has.
That's a fantastic question. So we have looked and we haven't succeeded. And the main reason for that is that in all of these examples that I showed, this operator also generates particle hole symmetry for you. So if it generates particle hole symmetry and you have zero energy, you cannot get to the ground state. But let's say now if you get rid of this fact that this operator will generate particle hole, then in principle you can pull this down and you can have like a volume law entangled ground state. But for us, it's like this is like fairly tightly constrained. So whenever this state exists, this operator also generates particle hole. And then because it's particle hole and our state is at zero energy, we cannot get to the ground state.
Hi, Steve. Can you hear me?
Yes, I can. Can you hear me?
Yeah.
Can you see me also?
I see you also.
Okay.
So would you share your slides, please?
Yes, let me just try to show my slides. Okay, is it visible?
Yeah. So, okay. So now it's visible and full screen. Okay, so let's start with the second talk by Sergej from the Hebrew University of Jerusalem, and he would be talking about multicriticality in even and odd Ising-Higgs lattice gauge theories. So Sergej, I'll give you a warning at say 35 minutes, and then you have like 5 minutes to finish.
Okay. Okay, hi everyone. So first, I would like to thank the organizers for giving the opportunity to present my work here today. Unfortunately, I was not able to participate in person in what looks like a very nice setting. And again, I would like to thank the organizers for being flexible and allowing me to present remotely. So despite presenting remotely, you're very much encouraged to ask questions somehow. I'll be happy to address them during my talk. Okay, so the story I will be sharing with you today revolves around a very classic framework in lattice gate series known as the Fredkin-Shankar model. And what I hope I'll be able to convince you is that despite this model being studied, I think, almost for the last 4 decades in general variant, it still holds many surprises that challenge our modern understanding of quantum critical phenomena. And in particular, as the title suggests, I will present some recent progress in trying to understand multi-critical phenomena in this model. So by way of introduction, I'm pretty sure you all are very much familiar with this model, but let's just quickly, just to set the language, quickly review the physics of the quantum Ising model, which would, interesting, would pop out throughout the discussion. So the basic setting, as you know, this being the spherical cow of Landau theory in quantum critical phenomena, is basically a lattice model of Ising spins, where we have two competing interacting terms, a ferromagnetic interacting term, which would like to align the spins to point in the same direction, and a competing transverse field term, which generates quantum fluctuations that would disrupt this representation in the computational basic. So the underlying logic of analyzing such systems a la Landau is, of course, to look for the symmetries of the model. And the model admits a global Ising symmetry, which basically amounts to a global flip of all the spins. Now, as you might know very well, the two terms here compete and would lead to two distinct phases and a quantum critical point. When we take the ferromagnetic coupling to be very strong, all the spins would like to align in the same direction, and I need to make a choice here. And for instance, here I've aligned all the spins to point up, and this basically breaks the underlying Ising symmetry. Now, as you crank up the strength of the transverse field, quantum fluctuations would eventually restore the symmetry and would form a quantum paramagnet where all the spins point in the positive X direction. Now, the key point of this analysis is very well understood nowadays, is that in order to classify the two distinct phases, one can define a local order parameter, which is, this case is just the magnetization, which is finite in the ferromagnetic state and vanishes in the paramagnetic state. And maybe more fundamentally, from a modern understanding of the renormalization group, it also controls the fluctuations near the critical point here marked by HC. Okay, so this is all very nice and very well understood. I'm pretty sure you didn't need this slide from the start, but this is also serves as a contrast, okay? So I guess in the last 20 or 30 years, we've seen an increasing number of instances, even starting to experimental instances, that go beyond this simple symmetry-based paradigm. And maybe the poster boy of this problem, which would also play a key role in all my discussion here today, is the toricode model. So much like the Ising model, here the degrees of freedom are Ising spins, but they reside on the bonds instead of the sides. And the toricode model consists of two terms. The first term is a star-like term, which is the product over the sigma x operators. And the second term is a plaquette term, which is a product over the sigma z operators belonging to each one of the plaquettes. And now I'll do something kind of violent to this model. I introduce two field terms, much like the transverse field model, but now also along the longitudinal direction, one along the sigma x direction, one along the sigma z direction. And the key point that by doing this, I've essentially broken all the symmetries of the model. So if we continue using Landau's prescription, we expect to see just a single phase and no phase transitions. But luckily for us, this is not the case. So if one actually solve this model, either numerically or you can do this analytically in several limiting cases, one can actually identify three distinct phases. So basically, we have a phase transition in a model without any symmetries. And the natural language to describe this, which I'll adopt, is an emergent gauge theory structure. And two transitions here, again, using the sort of high energy terminology, are confinement and Higgs transition. Now, there's one really interesting property of this model, which is not always emphasized, and again, will play a very important role in what I'll describe later on, is the fact that the model admits duality symmetry, very similar to the electromagnetic duality, which actually maps points along the diagonal part here where hx equals hz, okay? Now, just to show you that this is not just a fictitious model, maybe initially it was a fictitious model made up in a theorist's mind. I think now we are living in very exciting times that with the very rapid progress of both analog and digital quantum simulations, one can actually try to test some of those predictions in those artificial experiments. And we see some examples from neutral Rydberg arrays of realizations of a toricode-like model as an emergent low energy of Z2 spin liquid. One can even see dynamical properties of confinement on digital computers, and even encode the ground state of the toricode model and measure mutual statistics. And this is really a partial list of recent experiments. I should add a few more slides here as we go. Okay, so let me just, with a couple of slides, just give you the different phases here, and then we'll move on to some of our more recent results. So the simplest limiting case here is basically right at the bottom left corner, which is the toricode model. We take both field terms to 0, and it's very easy to see, and I'm pretty sure you've seen this at some point, that basically the Hamiltonian is the sum of computing projectors. And if I want to find the ground state, I need to individually minimize their energies. And this is taking a case where the product over all the star terms or the product over all the plaquette terms equals precisely 1. And later on, I would call this the vacuum state. And just as an interesting remark related more to the notion of error correction codes, which are very important in the use of the Tori code for quantum computing, is the fact that this does not fully fix the ground state. We still have two leftover qubits related to the two holonomies of the torus. And using the language of, again, of high energy physics, the logical qubits encoded here can be manipulated by those two string operators, which will pop up later on, which are also known as Wilson loops. Okay, so this is a very simple but interesting ground state. So if you want to play many body, we need to start considering excitations above this ground state, and those are induced by the two field terms. The sigma x term basically flips one of the spins and would generate two flux terms, two m particles. And repeated application of sigma x would allow me to start moving them around. Importantly, one remember their origin by a line of flip spins that would connect them. In a similar dual manner, we can generate e particles by applying the sigma z operators, which in the x basis would again flip a spin, and we can start moving them around. An important property, which will play a crucial role later on, is the fact that those two particles are fractionalized particles. I think it's kind of evident from the fact that they are created in pairs, and they admit highly non-trivial mutual statistics. In particular, moving an e particle about an m particle and vice versa would induce an Aronoff-Bohm pi flux phase. And lastly, as I advertised before, one can actually enrich this structure via a duality argument. So basically, if one exchanges the roles of the sigma x and the sigma z operator, geometrically, we also exchange the stars and plaquettes. So it seemed like we ended up at a completely different model. But it turns out this is just a lack of imagination, because the bonds of the direct square lattice are also the bonds of its dual square lattice. And quite nicely, after a simple visual inspection plotted here, you can see that the roles of the stars and the plaquette are interchanged between the direct and dual lattice. So basically, when we apply a duality transformation where we change the roles of sigma x and sigma z, we again obtain a toric model, but on the dual lattice. And basically, it maps, here marked by those two blue circles, it maps points mirrored along the diagonal that flips hx by hz. And this is a discrete version of the well-known E&M duality. And most importantly, for our case, if one now focuses on the diagonal line where hx equals hz, we obtain an enhanced Ising symmetry of our model, which leads to a self-dual theory. Now, let me now consider two limiting cases. One along the horizontal line here, which would lead to this emergent gate theory structure I advocated before. So in this limiting case, we basically expel all the electric charges, and the Hamiltonian, the resulting Hamiltonian has only two terms, the flux term and the transverse field term. The rest of the terms are basically frozen. And one can actually now construct kind of a dictionary where you can identify the sigma z operator with the electromagnetic gauge field and the sigma x operator with the electric field. And one can also construct a gauge invariant flux term. The electromagnetic gauge field is not gauge invariant, but the flux is, which is nothing but the sigma z plaquette term. Now, I call this a gauge theory, and we need some kind of a gauge symmetry. And the gauge symmetry is basically an Ising version of Gauss's law, which is defined only modulo 2. So basically, it's very easy to see that you have an infinite number of conserved quantities, which are nothing but the star term, which commutes with the Hamiltonian, and will lead to an infinite number of conserved charges, here denoted by QZ2, which are, again, identified with the E particles. So now we have two choices. We either have a vacuum, where we have no charges, and in this case, we have an even number of field lines that would emanate from each one of the sites. And by contrast, if we put matter fields or E particles, now the excess sources of the electric field, and we have an odd number of lines that come out of each site. And if you do the math a bit here, you can really see this is kind of an Ising version of Gauss's law. Just briefly to make connection with condensed matter, so this is a very natural occurrence that happens in constrained systems. Maybe the most famous problem is a dimer covering here of the triangular lattice. So in order to play quantum mechanics, I need to assign quantum numbers, and this is done by putting an Ising variable on the bonds, which tells us that it equals -1 if we have a dimer on the bond, and 1 if there's no dimer on the bond. And this leads to an emergent Gauss's law, because if we want to have only a single bond that will emanate from each side, the product of the sigma x operators would equal precisely -1. So now we're ready to understand what is the quantum critical phenomena that arise here. And let's take the limiting case here where the transverse field goes to infinity. So in this case, much like the transverse field Ising model, all the spins would point in the positive x direction. And I would call this a confining phase. The extra important ingredient here is the fact that we have a Gauss's law, which tells us that if now we imagine that we put two test charges at some distance, the only way to connect them and not pay a huge energy cost due to the transverse field term is to have a line of flip spins. The cost per spin is roughly h. So this means that we have a linearly increasing confining potential, which leads to confinement. In the other limiting case where the flux term dominates, here we have a zero flux state, and which I call a deconfining phase because the plaquette term would scramble this string and would lead to a very weak potential between two charges. Excitations above the ground states, which are gapped, are M particles. And the transition between the two states is dual to the three-dimensional Ising star transition, which I'll explain in a second. The two vanishing energy scales are the string tension that vanishes as we approach the critical point from the confining phase, and the gap for magnetic excitation as we approach it from the deconfined phase. Now, one can look at this transition from a dual prescription. Instead of expelling electric charges, we can expel magnetic fluxes. In this limiting case, the only remaining degrees of freedom are the charges, which I'll denote here by the new Ising variable kappa x. And some simple algebra can convince you that the resulting theory looks much like the Ising model we discussed before. The only real difference is that it has an additional link term between the Ising interaction, kappa z, which later on will play an important role. So this looks like an Ising transition, but actually it's an Ising star transition because the gauge symmetry tells us actually we don't have a global Ising symmetry, but only a local symmetry. And according to Elitzur's theorem, you cannot spontaneously break any gauge symmetry. And the transition here looks like an Ising transition, but I call it an Ising star because the entire critical theory is precisely the same, but we only take out operators that are odd under the Ising symmetry. Okay, so just to summarize all this packed information and move on to my results. So basically the summary of this even phase diagram goes as follows. At small values of the external field, we end up in a deconfined phase, which is kind of a deformation of the torical model. As we increase the strength of the transverse field term, we land in a confining phase where we proliferated the magnetic fluxes. In a dual language, when we increase the longitudinal field, we proliferate the electric charges and we end up in Higgs phase. And we have two Ising star transitions that meet at one multi-critical point. And the main focus of my talk here is trying to understand precisely what happens in proximity to this critical point. So in order to do that, I need to define a few observables, because as I said, we cannot detect any form of symmetry breaking here due to the gauge invariance. So the standard way to detect those confining transitions is via what is known as Wilson loops, which is basically a product over the sigma z or the sigma x operator around a closed loop, which will admit an area scaling in the confining phase and a perimeter scaling in the deconfined phase. Unfortunately, in the presence of matter fields, those observables are slightly ill-defined due to charge screening. So basically, in the confining phase, at some point, if you start increasing the size of the string, it pays off to introduce out of the vacuum two matter fields that would screen the interaction, such as both phases would now follow a perimeter law instead of an area law in the confining phase. So there's a very nice trick to circumvent this. It's known as the Fredenhanger-Markov order parameter, which is a ratio of half a loop and with two ends of electric charge with the square root of the full loop. So in principle, what this order parameter detects is the presence or absence of the screening mechanism that arises in the confining phase. And one can also define a similar observable for the magnetic loop by interchanging the roles of sigma x and sigma z. And the other observables I would like to mention is the breaking of the duality symmetry. So along the self-dual line, one can classify all the operators using their transformation under the duality. Since it's an Ising symmetry, it can be either an even or odd. In particular, let's for instance look at the energy density, whether it's in the electric sector in the sigma x or in the magnetic sector sigma x. So depending on if you look at the sum, which is the even, and the difference, which is the odd under the duality. And if one can actually measure, much like the spin stability, a response to self-duality by slightly perturbing away from that point, and we can even define susceptibility, which allow us to detect this difference between the two. Okay, so let's now focus on the main topic of my talk, which is what happens along the self-dual line. So there's abundance of literature on that topic, which many people tackle this problem from different angles, and roughly this is the story that is emerging. So again, at small values of h, this blue shaded area, we're in the deconfined phase, kind of a perturbation of the torical model. And as we crank up the strength of the transverse field, we end up in a new phase. And the first observation that the confinement and the Higgs transitions occur simultaneously. And this can be seen by a finite value of this Ferdinand-Markov order parameter, both in the electric and the magnetic sectors. The more surprising thing is that as we cross the transition, there's a spontaneous breaking of the self-duality symmetry breaking, which occurs simultaneously with the appearance of the confined and the Higgs phases. Now, quite interestingly, it seemed like that the critical exponent of the transition seems very similar to the U1 universality class. So nu is roughly 0.66. And this has led to many conjectures, and that it is possible that we have kind of an emergent symmetry at the critical point, that somehow those two Z2 star transitions combine together to give me an XY or U1 universality class. So of course, this is a very difficult statement to make without any knowledge of the underlying field theory description of the transition. And also, critical exponents can be somewhat deceiving. Okay, just one number that's supposed to characterize the full theory, but with the error bars that come out of any numerical techniques, one can actually misinterpret the universality class, especially if you don't know the full CFT spectrum. So this poses a numerical challenge for any exploration of this theory. How can we define this emerging critical theory without having some baseline theory to compare to? And so a really interesting method, which I like to advocate for here, is known as the real-space mutual information approach. So let me try to briefly explain what is the logic behind this approach. So one takes this lattice and divide it into three regions, here denoted by V, B, and E. So V is kind of a local region where you have your support of your operator, later on an operator as part of your CFT spectrum. You have some buffer layer which tries to eliminate the short-range physics, and you have a faraway environment where we will try to see if we can correlate the most with. The most important operators would have the smallest scaling dimension, which the weakest decay would be most relevant at the faraway environment. And the main ingredient here is to define this probability distribution function, this conditional probability distribution, P of H given V, which essentially it's kind of a coarse grain mapping, which would try to take the information contained in V and sort of compress it. Maybe just to give you suppose your operator's demagnetization, it would like to take, for instance, the average sum over all the spins. Okay, so this is basically kind of the rule of thumb of what this function does. And in order to find the most relevant operators, we would like to minimize the following functional. Let me try to explain. So the functional is a sum of two terms. The first term is the mutual information between the local environment V and H. And what this term does is tries to compress the information, or basically take the simplest operator as possible. And the competing term is the mutual information between this compressed observable and the faraway environment. It tries to check how relevant is this operator and how much it can predict on distant degrees of freedom. So basically, by increasing the value of beta, we basically increase the information budget. We obtain higher and higher order operators in our CFT spectrum. And since everybody likes machine learning, so machine learning actually plays a very important role here, not an obvious one. It turns out that the main technical challenge here is to really write down and optimize those conditional probabilities and those mutual information, and this is done very elegantly using modern machine learning techniques. So it's a technical detail, but an important one. So let's look at the results. So the main thing we'd like to examine is whether we have an emergent U1 symmetry. So we know that U1 is a continuous symmetry, so we expect to see a conserved current. And the key property of a conserved current is that it has a fixed scaling dimension. Okay, it's fixed by symmetry, and since we work in 3 dimensions, so it's deep -1 is 2. So we want to see an operator with dimension 2. So as a benchmark, let's start with a well-known example where 2 Ising symmetries transform into a U1 symmetry. This is the Ashkin-Teller model, which is 2 copies of a transverse field Ising model coupled via a bond-bond interaction. So here's the CFT spectrum. The y-axis is the scaling dimension, and the x-axis is the finite size scaling. So you see that as we increase the system size, we converge to a fixed scaling dimension. And we see we get a bunch of operators here, but most importantly, we can identify a scaling operator with dimension 2. And that's actually, in my mind, the most non-trivial result here, because we did not tell the computer that we have an emergent symmetry. It managed to discover a current operator with it's related to this conserved emergent current. Okay, so it's, in my mind, it's a highly non-trivial observation. So let's take this machinery and apply it to the self-dual Ising-Higgs model. So here we see the first 3 operators. The first 2 are, the lowest one is related to the breaking of the self-duality symmetry. The second one is the symmetric partner of it. And we also get a descendant. Okay, you see there's a difference of 1 between 125 and 225 for the symmetric and descendant. But most importantly, there's a missing operator. We don't see an operator with scaling dimension 2. Okay. So this gives us some confidence. Of course, it's always hard to justify a null statement, but given the ability of this program to resolve the emergent U1 symmetry in the Ashkin-Teller model, the fact that we have a missing operator here tells us that it is likely that the self-dual Ising-Higgs model does not belong to the U1 universality class. Now, I would like to even show you that, much of the criticism of machine learning is that those are black boxes. So let's try to shake the black box a bit and see if we can learn some physics. So actually, you can look at this conditional probability distribution and sort of pick out the prominent or the highly likable configuration, and they really match our intuition for what the operators should look like. And I would like to just highlight this emergent current operators that occurs in the Ashkin-Teller problem. So you can see here, The current operator is a product over something which is uniform in one of the Isings and a derivative in the other. This is precisely what we see here. So the computer really managed to discover this emergent current operator. So now let's tweak a bit this Tori code model. And as I said before, the even Tori code model worked in the background of vacuum. There were no anyons around. Let's look at the odd version of this model where we reintroduce our anyons to the problem. And this can be done very easy by flipping the signs of the plaquette and the star terms. So here, it's still a solvable model. It's very easy to solve it, but the ground state would now satisfy that the product over the stars and the product over the plaquette would equal -1 instead of +1. So visually, now we have a sea of E particles and M particles. So we have an E particle at each site and an M particle at each plaquette. And maybe by abuse of definition, I would call this a pi flux square lattice. Because I remind you that due to the mutual statistics, an M particle evolving around an E particle would accumulate a pi flux Aronoff-Bohm flux, and vice versa. So we have a pi flux both for the E and for the M particles. And if you want to go beyond this ground state picture, now excitations are kind of special. They are now holes of anyons and not the anyons themselves. So the key properties of this Tori code model is that actually it induces geometric frustration because there's an inherent competition between Gauss's law and the transverse field term. So the transverse field term would like to align all the spins in the positive x direction. But Gauss's law enforces us that at least one of them would point in the negative x direction. So the minimal energy resolution of that is to flip one of the spins, but this generates geometric frustration. You don't know which one to flip and how to arrange it in the lattice. The dual picture of that is basically the fully frustrated quantum Ising model, because in the mind of the E particles or the Higgs particles, we have an Ising model, but one where each one of the plaquettes has one antiferromagnetic bond, while the rest are ferromagnetic bonds, and this leads to, again, geometrical frustration. The resolution of the ground state is in the form of a columnar VBS pattern with this order parameter. Now it turns out that very close to the critical point, this fourfold anisotropy is irrelevant. And now it actually leads to an emergent U1 symmetry, but again, it's a U1 star symmetry because, again, we cannot explicitly break the symmetry. Okay, so let's try to summarize, at least in some limiting cases, the phase diagram of the odd Tori code model. So again, in small values of H and Z, we have an odd deconfined phase. And we have a confinement and a Higgs transition much like before, but they are accompanied by the appearance of valent bond solid order. And the critical point, the multi-critical point now is where two U1 star critical lines meet instead of an Ising star transition. Okay, so fortunately or unfortunately, I don't know, this is a far more numerically challenging model because due to geometrical frustrations, there's a numerical sign problem here. So instead of running a large-scale Monte Carlo's simulations, here we can only reach intermediate scale lattices using DMRG approaches. So let's try to look maybe at the global phase diagram using DMRG with 8x8 lattices. So first, let's look at the Fredenhagen-Markov order parameter. So indeed, we see that in the deconfined phase, small values of Hz, it's vanishing. So we're in a deconfined phase. But as we crank up the string fields, the field strengths, we obtain either a Higgs phase or a confining phase, depending if we crank up Hx or Hz. Now let's look at the VBS order. And very nicely, again, we see that in the deconfined phase, it vanishes. But as we crank up the string, the field strengths, we have a finite VBS order that occurs in tandem with the confinement and the Higgs transition. So that's the first conclusion. Higgs and confinement occurs together with VBS order. I would like to mention that you see this shaded region in the Ferdinand-Hagen-Markov order parameter, which has no columnar VBS order. So there might be some interesting physics here, which I will go back to it later on. So now let's look at the most interesting part, which is the self-dual line. Okay. So again, at small values of h, we're in the odd deconfined phase with a kind of a carpet of E and M particles. And let's, yes?
Yeah, you have like 5 minutes and then questions.
Okay, I think I'll make it in time. So let's crank up the strength of the field term. So here I'm looking at the Ferdinand-Hagen-Markov order parameter, which we see it rises roughly at 0.6. Next, I'm looking at the VBS order parameter. So we have confinement Higgs and columnar VBS. And very nicely, much like the even case, we also spontaneously break the self-duality symmetry. So this is a highly exotic phase transition, and to the accuracy of the DMRG, it seems like it's continuous. We see that all three order parameters rise simultaneously. Confinement Higgs, columnar VBS, and a breaking of the self-duality. Now, anticipating a quantum critical point, we expect to see some softening of energy scales. And indeed, if you look at the first excited state gap from DMRG, it softens roughly near the transition. And we also did some interesting small scale, low energy exact diagonalization, where indeed we see that what drives the transition is a mode at 0 pi, exactly the VBS order. So as I alluded before, this is not the end of the story. If you keep cranking up H, you eventually lose the columnar VBS order. And one can see here that as I increase the strength of the field, I start to see VBS pattern with an increasing unit cell. So this is reminiscent of what is known as the Devers staircase scenario, known from quantum diamond model. And indeed, we see a series of first order phase transition here plotted, for instance, for the sigma X operator, which suggests a rearrangement of the lattice until it completely gives way to a quantum paramagnet. So just to summarize, I gave you some indication using the real space mutual information approach on the absence of a current operating even Tori code model, which is at odds with an emergent U1 symmetry. I've revealed a quite interesting multi-critical phenomena in the odd Tori code model where Higgs confinement, duality symmetry breaking, and columnar VBS occur simultaneously. And we've also revealed a VBS cascade scenario in the problem, which is driven by geometric frustration in the odd Tori code model. And I would like to give credits to Zohar Ringel, my colleague from the Hebrew University, and our student Lior Oppenheim worked on the even Tori code model using the machine learning technique, and also to my very talented PhD student Ayush De, and my very talented former postdoc Umberto Bora from LMU, who worked on this odd Tori code model. Okay, thank you.
Questions?
Hi, Snir.
Hey, Sergej.
I have a question about this U1 star. So
U1 star.
in that odd case.
Here.
So did you try to use this machine learning technique to see that emerging?
So that's actually a very good question. So the data here is DMRG data. So basically, you get a ground set wave function. So one of the things we're trying to do now is to sort of sample this wave function and try to see if it can give us any information on the the ground state wave function using this machine learning technique. So it's work in progress. It's actually highly non-trivial because it's not classical information. It contains entanglement, etc. So it's.
Can you tell a little bit more about the method? What kind of data you need to put in?
So what you put in is right here. So essentially, what you put in the because you want to generate those probability distribution functions. So what you put in is our Monte Carlo samples, basically, which are sort of representative of the configuration space. In the quantum mechanical setting, the analog would be to basically look at the respective weights of different spin configuration in some given basis. But actually, that's not fully revealing because, as we know, we have interference, etc. So it's one of the things we're trying to do is sort of extend this notion also to numerical approaches that use the quantum mechanical wave function, not Monte Carlo samples. So it's slightly different. Hope it's clear. Yeah.
I might have missed this when you explained previously, but can you explain why the presence of an operator with scaling dimension 2 tells you the emergence of U1?
So okay, so if you have okay, so if you have an emergent U1 symmetry, it means that you have a current operator, right? Because if you have a continuous symmetry, so you must have a current operator that comes along with it. It's a theorem, and that's our theorem. Now, okay, so I don't have a blackboard, but it's kind of a one-liner to show that the scaling dimension of a current operator must equal 2. And the way to look at this is via charge conservation. Basically, if you integrate over J naught, you must get the global charge, and under scale transformation, the global charge does not change. The integration measure changed by d minus 1, and you get scaling dimension d minus 1. Okay, you can. So this is sort of fixed by the definition of this being a current operator for conserved charge. Yeah, I hope it's clear. Maybe we can discuss this offline now.
This is Subhro. I had a question regarding this emergent U1 in the even case. So
in the even case.
Yeah. So
here or
yeah, or lack of it.
Lack of, yes.
I mean, why in the first place would you even expect a U1? Because the two Z2s that you sort of indicated are not really independent Z2s. So they are one.
No, you're completely right. So this I put a lot of question marks here. Yeah, you see there are like 5 question marks on this slide because it's I think people conjectured it because it's has this flavor of Z1 times of Z2 times Z2. And the critical exponents are closed, and so it's I got a null result. It doesn't mean that I didn't overrule this. I didn't suggest a new theory, so it could still be a U1 universality class. But I guess the missing link here that, to best of my knowledge, no one has written down a field theory that would explain all of those transitions. So the true answer is that I don't know, but I have some supporting evidence that potentially this is not the case. So maybe just to refine my argument, yeah.
Hi, Sneer. It's Julian.
Hey.
I have a question. Can you update us about the status of this perturbation analysis that you were about to think about for the...
It's done. It's done. It's ready.
It's done. Okay. That's the only update you can say. And I have another question. So when you study the out case,
yes,
of course you need some constraint on the system sizes, right? Because you need
right.
Lx times Ly to be an even
precisely.
number. Did you try to see what happens if it's an odd number? Because in that case, you will have some sort of holes which will be here and which might give rise to some non-trivial zero mode. And I was just wondering how would it affect your phase diagram?
It's an excellent question. I did not try this. It's a very good question.
Thanks.
Yes.
Hi, Sneer. This is Benoit. Hello.
Hey, nice to see you.
Nice to see you virtually. I was curious actually whether you attempted to look at a sort of mixed oddity theory, in the sense that you put an array of flux tubes, but you don't frustrate the Gauss law. I have the impression that could be very interesting to investigate the Higgs transition in the presence of a small h and perhaps finite hx, because the idea is that if the flux lattice is spinned, thinking in analogy with superconductivity, Abrikosov lattices, it doesn't destroy superconductivity, so you expect a Higgs phase. But if for some reason the lattice unpins, and that could be the result of activating a small hx, you would destroy basically the Higgs phase. So there might be, of course, you completely lose all these beautiful self-dualities in that setting, but the physics of the Higgs, transition, for example, can be rather intriguing.
Yes, that's a good question. And just to even strengthen this, there's actually no sign problem there. So you can actually investigate this to very large systems. So it's on some to-do list, and but it's a very good point. And also the multi-critical point, even though you lose the self-duality, could still be very interesting. I don't see any, it would be a U1 star connecting an Ising star. It could be, I don't know, it could be a very interesting transition on its own. It's a very good point. Yeah.
Okay, if not, let's thanks Sergej
Okay,
once more.
Thank you very much. Unfortunately, I'm not able to attend there. It seemed like a very nice meeting.
Okay.
Okay, bye for now.
Yeah, bye. So, yeah, so that's it for today, and we'll be back tomorrow at